Hello, I'm Susanna, and my PhD topic is spatio-temporal modelling of cancer data in Queensland using Bayesian methodology. Queensland covers an area of almost 2 million square kilometres and has a population of 4.4 million people, with the majority concentrated along the coastline, particularly in the southeast corner. It's famous for its beaches and laid-back lifestyle, but has the highest cancer incidence rate of any state or territory in Australia, largely due to its high incidence of melanoma. Each year in Queensland, around 20,000 people are diagnosed with a primary invasive cancer. This number excludes the common non-melanocytic skin cancers. Previous research has shown that certain cancers have geographic discrepancies for incidence and survival within Queensland. 14 regions were examined using empirical Bayes methods. The point of this research project is to examine smaller regions than before. We are going to divide Queensland into 478 regions. This will allow us to understand where are the discrepancies, what may be influencing these, have they been changing over time, and how they can be addressed. Bayesian methods are commonly used for disease mapping analyses, and we've chosen to use Bayesian hierarchical models. Advantages of hierarchical models include producing estimates which incorporate more of the uncertainty, drawing strength from neighbouring regions, so those with few cases can still produce robust estimates, and greater flexibility in the model. One commonly used model in disease mapping is the Biseg, York and Mollier, or BYM model. This model has yi following a Poisson distribution, with mean EI theta I, where theta I is the rate and EI as the population size. Theta I has alpha as a constant, UI as the correlated heterogeneity or the spatial clustering, and VI as the uncorrelated heterogeneity. Due to the complexity of the model once priors are included, Markov chain Monte Carlo algorithms are used to sample the posterior distribution via either Gibbs or Metropolis-Hastings samplers. This model was originally developed for image resolution. There are similarities between image resolution and obtaining a clear relative risk of cancer incidence in small areas, as they can be thought of as involving an underlying spatial component of interest corrupted by observational noise. Nonetheless, there are concerns associated with this model, such as the potential for oversmoothing and sensitivity to the choice of priors. There have been additional refinements and variations to this model proposed, but ultimately we may consider producing a new model specifically geared towards mapping cancer data. So once we've clarified what cancers have adverse outcomes and where these are, we will explore what factors may be influencing these. Characteristics we're intending to investigate include area disadvantage, urban versus rural and remote, time period, and distance to treatment. We'll also examine the effect of individual factors such as socio-economic status, as estimated by occupation, ethnicity, and for certain cancers, information about cancer stage at diagnosis. The results of this project will guide the development of more effective diagnostic and screening practices, health policies, health promotion programs, and other interventions aimed at reducing spatial and temporal inequalities for people diagnosed with cancer. By using complex Bayesian models, we can determine where the inequalities are and what is influencing them, which allows them to be addressed. I would like to thank my incredible supervisors, Kerry Mengerson, Peter Bardi, and Tony Pettit. I would also like to acknowledge the Bertel Centre for Research in Cancer Control at Cancer Council Queensland and Queensland University of Technology.